Everyone, welcome to today's lesson. So today we're looking at dynamics. Then the topic is kinetics of particles, and to be specific, we're looking at kinetic of particles of rigid bodies. My name is Harmtedy. This is lecture 2. Then we're looking at planar kinetics of rigid bodies, and then at the end of this lesson you'll be able to know how to calculate the moment of inertia of a body, and you should also be able to know how to develop planar kinetics of equations. Kinetic equations of motion for symmetric rigid bodies. And then you should also be able to discuss the applications of these equations that we're going to discuss, undergoing translation, rotation about a fixed axis, and general plane motion. So kinetics of particles. So we first need to understand one thing here. For instance, if you have a body which has a fixed size and shape, an applied non-concurrent force system can cause the body to both translate and rotate. And then if you remember very well, we talked about finding the force of a translating body. Now in this case here today we'll look at the moment of inertia, which is just going to describe what happens, or it's going to describe the forces that occurs when a body is rotating. So in other words, we are just going to look at the rotational aspect of motion of a body. So we were that if you remember, this F is equal to MA. This one just talks about a translating body, meaning it's just moving either in the X, Y, or Z axis. But when we talk about rotation, we have to include what is called the moment, represented by the letter I. This is the moment of inertia. The moment of inertia, which is represented by the letter I, and then moment is just moment is represented by the letter M, capital letter M. So the translation aspect of motion were studied in the previous session and are governed by the equation. So this equation is the one that governs the translation aspect of motion. And then it will be shown in the next session. In what we're going to start doing, we're going to show the rotational aspect of motion, which is caused by the moment M, and it is governed by the equation M is equal to I alpha. So this alpha is just the rotation acceleration. So if you remember very well, in the previous session that we had, we said this M can also be called can also be called the moment of inertia of a body, because it's just the resistance of an object to the change in its acceleration, in its translation acceleration. But in this case, when you talk about rotation acceleration, we're simply discussing, or rather we're going to use, instead of using M, we're going to use I. So this formula and this formula are just one and the same. The only difference is that here we're dealing with rotation, with the rotation aspect of motion. Here we're dealing with the translation aspect of motion. So the symbol I in this equation is termed the mass moment of inertia. So I, you can hear, even there is also an aspect of mass here, which is just this mass there. So that's why it's called the mass moment of inertia. Then by comparison, the moment of inertia is the measure of the resistance of a body to angular acceleration. So the moment of inertia of a body is just a measure of the resistance of the body to angular acceleration. That's the reason why you're using angular acceleration here. And then you remember how we defined mass. We said it's just a measure of the resistance of the body to translation or linear acceleration, translation acceleration. Okay, so in the same way, that mass is the measure of the resistance of the body's resistance to acceleration, which is just translation acceleration. Yeah, this is what I've just been talking about. Then let's quickly move on and see what this is. So imagine that we have this body here, and then this r is called the moment arm, r, which is the distance from the center of rotation to the to any chosen part, or to any chosen part of the body, which is called dm, or to any chosen mass of the body called dm. So for composite and irregular bodies, the moment of inertia as the moment of inertia as the integral of the second moment, sorry, about an axis of all elements of mass dm which composes the body. So in other words, what they're trying to say here is the moment of inertia for a composite and irregular body, meaning the body that whose shape you can't define. Yeah, so if you have a shape that is not definite, at least for shapes which we know to say, maybe what's this, when you have something like this, yeah, when you have something like this, when you have definite bodies, the moment of inertia is easily found. But when you have a body that has no definite shape, if you have a body like that, you can find the moment of inertia. The formulas have already been derived, so you just have to plug in the values that you have been given. Now if you are dealing with a body like this one, and then you don't know the shape, you don't know the shape of this, what you use is integration. You find the moment of inertia by integrating. And then how do you integrate? At least you get one part, a small mass out of this whole mass. You just take a small mass, that one you're just going to call it the change in m, which is just dm. It is then known that if you want to find the moment of inertia of this whole body, you just get this small part, and then this small part you call it dm. Yeah, I've just repeated what I just said again. You call it dm, and then you integrate. You find the integral. Of respect. You take the lower limit to be m, and then this one should be r squared, and then dm. Okay, so this is what I'm just trying to talk about here. This is the formula for the moment of inertia of an irregular body. So you just find the integral of the moment arm squared, then you differentiate, you integrate that with respect to m. So here the moment arm r is the perpendicular distance from z axis to the arbitrary element dm. If the density of the body rho is given, and the body volume change along the axis of rotation, then dm is equal to dv, is equal to rho dv. So we know to say density is given by mass over volume, which can also be written as mass is equal to rho dv. So they are saying if the volume change along the axis of rotation, so if the volume of this mass that you've taken, arbitrary element that you've taken, if its volume is changing, it means that sorry, this one can be written as I was supposed to say, this one can be written as rho m is equal to rho v. And then if this volume is changing, if for instance we say this is changing, the volume is changing, the mass will also be changing. Hence we have dm is equal to rho dv. So this is what they are trying to talk about there. So now if you have this, don't you think that you can replace it while there's dm in this equation? Meaning you are going to have the moment of inertia to be equal to the integral of r squared. While there's dm, we put rho dv. So this now changes. You can integrate this r squared with respect to v. So this rho is a constant, so meaning you can remove it outside and just integrate r squared dv. So this is what you simply have to know. Okay. So I is given by, so the moment of inertia can also be written in this format, where you say the integral of r squared rho dv, and then the initial volume is going to be our lower limit. Okay, same applies to this. They've just removed the density outside. So let me just talk about this. So this is what we are talking about. You choose this arbitrary element dm, which is dm, and then we found to say dm can also be written as rho dv. Yeah. So these x and y are just showing the position on the x or y z plane. So let us now see and learn how you can obtain the moment of inertia by integration. Let's check. So you have two methods by which you can obtain this moment of inertia by integration. There is what is called the disk element, the disk element and the shell element. So to obtain the moment of inertia by integration, we will consider only symmetric bodies having volumes which are generated by revolving a curve about an axis. An example of such body is shown in the figure 17.2a. Let me show you the figure they're talking about. Yeah, 17.52a. Sorry, this one is B. Oh yeah, it's this one. Okay, I forgot to put the diagram here. Alright, so two types of different elements can be chosen. So we can choose what is called the shell element. I'll explain. Even without a diagram, I'll explain. So if the shell element having a height z and radius r, which is equal to y, and the thickness dy is chosen for integration, then the volume is, so we know to say volume. So if you choose the shell, element, you need to say the volume of this shell is going to be V is equal to pi r squared h. So volume is equal to pi r squared h, and then let's now replace in the values that we have. Or before we do that, let's find dv dr. Or in this case first, our r is what? We need to say our r is just equal to y. So while there's r, let's put y, and then while there's h, we can put z, because our h here is z, then our r is y. So while there's r, let's put, so say v is equal to pi, our r is simply just y squared, and then our height is z. So now let us find dv dy. I want to find the change in the volume. So this is just going to be 2 pi y, and then z, 2 pi yz, and then 2 pi yz, when we cross multiply here, we're going to have our dv to just be equal to so our dv is just going to be equal to 2 pi y z and then dy after cross multiplying. So this is what you are going to have. This is what you are going to have. 2 pi yz dy. This is what you are going to have. This is your dv. So when you look at what has been given here, I was just trying to derive this formula for you. Yeah. So they are saying if you choose a shell to find the moment of inertia, in the formula I is equal to rho r squared v and then dv. While there is dv here, you simply just have to replace this and then you integrate, and then after integrating, and then while there is r, in this case our r is y, so meaning here you say y squared. So what you do here now when calculating, while there is dv you put this part, then while there is r you put y, and then you integrate. Once you integrate, you find your final answer, which is the moment of inertia. So the element may be used in equation 17.2 or equation 17.3, which is just the equation that I showed you here, which is the moment of inertia is equal to rho the integral of r squared dv. So when the shell element is used, you can use this equation to determine the moment of inertia about z of the body, about the z-axis. Yeah, since the entire element, due to its thinness, lies at the same perpendicular distance r, which is equal to y from the z-axis. Yeah, so you can either choose the shell element or you can choose what is called the disk element. You see on the next page, you choose what is called the disk element in order to find the moment of inertia I. But when you are using the disk element, you always you not use this formula. Sorry, you not use this formula. I'll show you what to use. So let's look at the disk element. So if a disk element having a radius y and the thickness dz is chosen for integration, then the volume is dv, which is equal to pi y squared dz. So the volume dv will change now in this case. So the dv will change. In the previous one we used this as our dv, but when you look at this, this one is different from this one. So the dv will change to not be exactly as it was. Why? Because here we are using this shell. Sorry, we are using this disk. Then when you look at this disk, it's looking as if it's a cylinder. It's in this format, meaning you can easily find the volume of this cylinder. The volume of this cylinder, meaning the change in the volume, since this one is going to be changing. Here it will be like this. On the next one, it's going to have another radius, and then on the other part again, it is going to be another radius. Meaning this one is going to be changing its radius. So meaning what will not write volume, but to say the change in volume. So the change in volume will just simply be equal to the base area. We know to say volume is just base area times height. So what is our base area? Our radius there is y. So our base area is just the circle, which is pi r squared. So pi r squared, our radius is y. So we'll say pi y squared, and then our height, the volume is just base area times height. So our base area is a circle, and then times our height is dz. So our height is dz. So we say pi y squared dz. So this is the dv we are going to use for the shell element. So for the shell element, it's going to be the dv is going to be different from the one that we use on the for the disk element. The dv is going to be different from the one that we are using here on the shell element. So let's read these notes. This element is finite in the radial direction, and consequently its parts do not all lie at the same radial distance from the z-axis. As a result, equation 17.2 or equation 17.3 cannot be used to determine I directly. Instead, to perform the integration, it is first necessary to determine the moment of inertia of the element about the z-axis, then integrate this result. Okay, so to determine the inertia, or to perform the integration, it is necessary first to determine the moment of inertia of the element, meaning you first find the moment of inertia of this cylinder here that you've gotten, which is a disk, about the z-axis, and then integrate the result that you're going to have. So let's look at this example here. Instead of us just talking, we need also to look at one example. So, okay, the example says, determine the moment of inertia of a cylinder shown about the z-axis. The density of the material is constant. So now look at this. This is a cylinder, and we've decided to use a shell element for us to determine the moment of inertia of this cylinder about the z-axis. So we're trying to determine the rotational aspect of this cylinder about the z-axis. So we're going to use what we call the shell element, and then this problem can be solved using the shell element at a single integration. So the volume of the element dV is just given by this. Remember, on the shell element we said dV is just 2 pi r h dr, so that its mass dm is this. So the mass is just this, which is written here. The mass is equal to that, which is dm is equal to rho dv. You remember this, we derived these formulas. Since the entire element lies in the same distance r from the z-axis, the moment of inertia of the element is going to be di. So di z is equal to r squared dm. So I, we know to say I about any axis is just given by r squared m. R squared m, that is I. Now since the moment of inertia here is changing, so we say di about z, the change in I about z is equal to this moment arm is constant, so we just say r squared, and then the mass or the arbitrary element will also be changing. So now we know to say dm is given by this. So while there is dm, we can put a rho dv, or we can put this. So here we are using h, we are using h here. So I'm not using y or z, using h in this case. So while there is in this expression, while there is dm, we simply replace with that, then we have our expression to look like this. The expression will look like this here. So hope you're getting what I'm saying. And then after that, we can now perform the integration. So when you integrate this part, we're going to remain with just iz, and then we also integrate this part. So when integrating this part, we know to say we're integrating this with respect to what? To r. So meaning all these others will remain constant. So meaning all these other will remain constant. So meaning they can even be removed outside. This is what has happened here. You remove them outside, just remain with r here, and then you integrate this with respect to r, meaning you are going to have r to the power 4 divided by 2. And then when you simplify the expression, you have something like this. Okay, so having found the moment about z, we can now say, let us just simplify this to its simple form at least. So we can now say the mass of a cylinder is just equal to the integral of dm. We know to say, when I say we already have what we have here is the m. We don't have the mass. We don't have the mass. We only have the change in mass. So if you want to find the mass, we need to, since this is the derivative of m, if we want to find the mass, we need to find the integral of that in order to find the mass. So this is what they are saying here. So what we've been given in the question is just the m, which is the change in mass, but we don't have m. So to find m, we need to integrate the m, taking the lower limit to be the mass. And then when you do that, and then we know to say the m is just given by this. So we put that there, and then when we integrate this with respect to r, you are going to discover that you have this as your answer. So having found this, so meaning this is your mass, this is your mass, and then in this expression you can now make h the subject of the formula. So when you make h the subject of the formula, you are going to have h is equal to m over rho pi r squared. So this expression, you take it and then replace it where there's h. So when you replace it where there's h, you can see it to say you have rho will cancel with that rho, you have this pi will cancel with that pi, and then you have this r squared will cancel with at least r squared there, will remain with r squared there. So meaning the moment of inertia of this body about z will just now be given by half, we've remained with m r squared. So this is the moment of inertia of a cylinder. Let's see. Yeah, so this is what I was just talking about. So this is the general formula for the moment of inertia of a cylinder. So all you need, if you want, you can master this, but sometimes they give in an exam room if you've forgotten. So this is the moment of inertia of a cylinder. Yeah. Let's look at example 2. So example 2 says if the density of the material is 5 slag per feet cubed, determine the moment of inertia of a solid in figure 17.4a, which is just this figure here. Determine the moment of inertia about the y-axis. So first of all, you need to decide what you are going to use. So sometimes they will not give you this diagram, they will just give you this diagram. So meaning what you need is to identify, are you going to use a disk element or a shell element? So now since we know to say there is this diagram here is small at one point, is small on one side, and then it's big on the other side, and it's in a circle form. So instead of using a shell element, which works well when you're dealing with at least a uniform object or a uniform element, you can simply just use a disk element, because a disk, this one will be growing. Here it's having this radius, on this part it's going to have a different radius, and then finally on the other part it's going to have a different radius, and then you integrate. So what you're going to do here, you take your height there to be dy, and then the distance from this point up to there to be y, and then we've been given to say this one is 1 feet, and then this is also 1 feet, and then this is our origin O, and then we also know to say this distance from there to there is x, as we'll call it as x, sorry, yeah, we'll call it as x, and then the height, we just say the change in the y, because this one is changing and the x is also changing. So let's quickly use the disk element. So the moment of inertia will be found by the disk element as shown in figure 17.4b. Here the element intersects the curve at the arbitrary point xy and has the mass dm, which is equal to this. So this shell element, we know to say the dm of this element is given by that. the dm here, the change in the mass is given by that, which is, and then we know to say dv, when you're using the disk element dv, we found it to be, if you remember very well, let me just go back. Okay, here, this is our dv that we found, if you remember very well. So you need to know these formulas, or you need to know how to derive them if you don't want to master it. So while there is dv, we replace with pi x squared. In this case our radius is x, so we say pi x squared dy. That's our dv. So from there, this is our dm. We now quickly we know to say the moment of inertia of a cylinder, we just found it in the previous question, is given by half mr squared. This is the moment of inertia of a cylinder. Let us now find the moment of inertia about the y-axis of this object. So we know to say diy is half dm. So here, instead of using m, you say dm and then x squared. So our radius here is x in this case, so this is why they've used x squared there. Then dm, this is our mass is changing, so it's not a fixed mass. If you have a cylinder which has a fixed mass, you just put your mass there, but here our mass is changing since the cylinder grows as it goes up and then it reduces as it goes down, so meaning the mass changes. So we say dm, and then on dm here we're going to replace with this part. We're going to replace dm with that part, so this is what we're going to have, and then our x squared there. So here, from here, we can now integrate. Yeah, we can now integrate given these substitutions. We know to say x is equal to y squared. This is the equation of the curve we've been given. So you can either use x or you can either use y squared, but when you use y squared, it will be another thing. You're going to, yeah, when you use y squared, even the limits have to change. Okay, so iy is just found by the integral of x to the power 4, or you can integrate when you put y to the y squared here, meaning this is going to be y to the power 8. Yeah, so which is just this part. So if you want, you can use this, you still find the same answer, or if you want, you can use that, you still find the same answer, which is that when you punch it on your calculator, you find this as your answer. So this is how simple these things are. You need not to be stressing for you to solve such questions. They are simple and straightforward. You just have to be patient and know what you are using, know which formula you're going to use, know which element you are using, is it the disk or the shell element, and then know how to apply them. So let us now look at the parallel axis theorem. So this one is just a theorem that is going to be used to find the moment of inertia when at least you have if you want to determine the moment of inertia of a given mass, and then given the center of mass of any of any other of any other axis. Yeah, okay, let us read through these notes. If the moment of inertia of a body about an axis passing through a body's mass center is known, so when you know at least the moment of inertia of okay, let's look at this diagram so that you know what I'm talking about. So if you know the moment of inertia about this center, then the moment of inertia about any other parallel axis. So the moment of inertia about any other parallel axis to this center, any axis parallel to this center of mass, can be determined by what is called the parallel axis theorem. So this, we're going to derive the theorem, we're going to derive it. So we know from this, just from this expression here, to say, using Pythagoras theorem, to say r squared, if you want to find the r squared, this one can just be found by adding the square of this and that. So this one here down is just d plus x prime, and then this one is y prime. So when you find d plus x prime squared plus y prime squared, you find r squared. So the moment of inertia, we know to say it's given by this formula, and then dm we know, then we are going to replace them at the end. But r squared we know to say is just this part here. So meaning while there is r squared in this formula, you replace with d plus x prime squared plus y prime squared, and then you write your dm outside like that. So now this is what you are going to have. So when you're integrating, you can first expand this. So when you you can first expand this part. So when you expand this part, you are going to have this part. You also have 2 dx prime, but since we are integrating this with respect to m, you only get x there. Then you have d squared when you expand this part, and then you write your dm that side. And of course there is this y squared plus x prime squared plus y prime squared. So there they just expanded that part, and then they separate, they split, rather they what's this, they distributed this integral symbol. So since r squared plus x squared plus y squared, okay, since r prime squared is equal to x prime squared plus that, the first integral represents ig. So this is this one is the moment of inertia about the center G. Yeah, so because we know to say this r prime here is just equal to x prime squared plus y prime squared, which is just representing ig. So when you work out this one is just called ig, the moment of inertia about the center G, about the mass center G. And then the second integral is equal to 0. Why do we say this is equal to 0? Since the z prime axis passes through the body's mass center I, yeah, so it passes through the mass center. Since z prime, which is this one, passes through the mass center, so meaning when you take the limits there, the final limit and the initial limit, the limit which is supposed to be here and the initial limit that is supposed to be here, when you find them, or rather let me not use the limits, since actually they are all zeros, when you find the limits, the limit that is supposed to be the upper limit and the lower limit, when you find the upper limit and the lower limit and then replace them in the integral of this, you eventually find a 0 as your answer. Then this one, which is the third integral, the third integral is just this one, which is just known, we know to say this one is just the moment of inertia of any body. Let's look at it, because this one, when you integrate this with respect to m, you simply just have m. So meaning you are going to have m d squared, which is just the moment of inertia of the body there. So now to find the moment of inertia of the whole system there, you just remain with ig, and then plus the moment of inertia of that given body. So meaning you first find the moment of inertia of a point that you've been given, and then you find the moment of inertia of that other body. So ig in this formula represents the moment of inertia about the z-axis passing through the mass center G, and then m is the mass of the body, then d is just the perpendicular distance between the parallel z and z prime axis, which is just this distance. Alright, so I think this is the end of today's lesson. If you have any questions, you can simply just send them through on WhatsApp. I'll explain properly so that you understand where you thought maybe you never understood properly. But before you ask, this is a video, you can play it back and see if you still not understand for the second time. If you fail to understand for the second time, that's when you are free to contact me. And then I think this is the end. I'll send an exercise when sending this same slide. Thank you very much for watching today's lesson. Shalom, shalom.